Hello, welcome to Rational Functions. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This is for Math 1508 at UTEP. Chapter 2, Polynomial and Rational Functions, comes to us from Larson's 10th edition pre-calculus text. Section 2.6 is all about rational functions. Let's start with an informal definition. A rational function is a quotient of polynomial functions. Rational, ratio. Rational function's a quotient. Okay. A rational function can be written in the form f of x equals n of x over d of x, where n of x and d of x are polynomials, but d of x is not the zero polynomial, and we use these quite cleverly for numerator and denominator polynomials. In general, the domain of a rational function includes all real numbers except those that make the denominator zero. When it comes to rational functions, we have these things called asymptotes. The line x equals a, and it's a line, so it has to be the equation of a line, something on the left, an equal sign, and something on the right. The line x equals a is a vertical asymptote of the graph of f. If f of x goes to infinity or to negative infinity, as x gets closer to a, either from the right or from the left. And a little note on notation here. Think about a number line, and on a number line, we have positive values to the right of 0, and we have negative values to the left. And so sometimes we'll use a notation, x approaches, make that an arrow there, a, and we'll put a positive up here, and the positive just means from the right. And we'll put an x approaches a little negative up there, that means from the left. So notations that we use frequently in calculus, but they're never really defined here, and we should keep that in mind. The negative part of the number line is on the left, so that's from the left. Positive part of the number line is on the right, so a little positive superscript is from the right. The line y equals b is a horizontal asymptote, again a line, so it's equation of a line, is a horizontal asymptote of the graph of f if f of x approaches the number b as x goes to positive or negative infinity. We'll frequently call the horizontal asymptote the end behavior because I want to know as x gets super large and positive or super large and negative, what's happening to the y values. So horizontal asymptote, also known as end behavior. Very important to remember, asymptotes are always equations of a line, never just a number. 7, never going to be a horizontal asymptote. Y equals 7, could be. So, let f be a rational function given by f of x equals n of x over d of x. And the numerator is just some polynomial with degree n. The denominator is just some polynomial with degree m. We're going to assume the n and d have no common factors. The graph of f has vertical asymptotes at the zeros of d of x. So if there are no common factors, then the zeros of the denominator will give us the equations of the vertical asymptotes. The graph of f has one or no horizontal asymptotes determined by comparing the degrees of the numerator and denominator. If the degree of the numerator, n, is less than the degree of the denominator, m, the graph of f has the line y equals 0 as a horizontal asymptote. For now, memorize it. If you want to know why, check out my lecture on infinite limits, or limits at infinity from Calculus series, Math 1411 if you're looking for it in the UTEP numbering system. If n equals m, so the degree of the numerator is equal to the degree of the denominator, the graph has the line y equals, and then the leading coefficients, a sub n over b sub n, as a horizontal asymptote. If the degree of the numerator is larger than the degree of the denominator, the graph has no horizontal asymptotes. It might have other types of asymptotes, but it won't have a horizontal one. All right, remember these, just know them for now. With calculus, we can prove why these are true. So let's find the domain of the rational functions and identify any vertical or horizontal asymptotes. The domain only cares about the denominator. This particular rational function is completely simplified. The numerator and denominator have no common factors. So for the domain, x minus 2 all cubed cannot be 0. My denominator can't be 0. Well, if something cubed can't be 0, then the x minus 2, cannot be 0. And if you prefer, take the cube root of both sides. X minus 2 can't be 0, so x can't equal 2. We might also say the domain consists of all real numbers except x equals 2. Don't use a double negative there. If you use the word except, then it's equal to. Otherwise, you just say x can't be 2, but it could be anything else. The vertical asymptote, which is closely related to the domain. Remember, the vertical asymptote is what we get when we set the denominator equal to 0. Domain not equal to 0. Vertical asymptote equal to 0. The degree of the numerator is 0. There are 0 variables here. The degree of the denominator is 3. If I were to multiply this out, I'd have an x cubed. Since the degree of the denominator is larger than the degree of the numerator, y equals 0 is the horizontal asymptote. In the polynomial 3 minus 7x, we have it written in non-decreasing form. It's kind of frustrating for some of us. Over the polynomial 3 plus 2x, if it helps, rewrite it in a nice decreasing order of power. That's an ugly 3, but still a 3. See if I can make this one prettier. There we go. If it helps, rewrite it. Now the domain is where the denominator is not 0, so 3 plus 2x cannot be 0. Subtract 3 to both sides. 2x cannot be negative 3, so x cannot be negative 3 halves. Domain, x cannot be negative 3 halves, tells me my vertical asymptote is x equals 3 halves, the equation of the line. Degree of the numerator is 1. Degree of the denominator is 1. Since the degrees are equal, the horizontal asymptote is y equals a negative 7 halves, the leading coefficients of both the numerator and denominator. For f of x equals 4x squared over x plus 2, the denominator can't be 0, so x cannot be negative 2. The domain leads directly to our vertical asymptote, the positive version, x equals negative 2. Since the numerator has degree 2, the denominator has degree 1. Remember, degree is the highest exponent in the polynomial. There will be no horizontal asymptote for this particular function. Okay, so we're going to graph some of these, and we're going to draw the graph without the use of a calculator. We're going to pretend we have absolutely no electronics or technology at all, and we could still do this. Let f of x be n of x over d of x, where n and d are polynomials. First thing you're going to do is find the domain of f by finding the zeros of the denominator. Now, after you do that, my next step would be to completely factor the numerator and denominator and lay them out in factored form. We're going to find the holes in the graph of f by finding the zeros that the numerator and denominator have in common. So a common factor in the numerator and denominator will lead to a hole in the graph. In calculus, we'll be able to plug these holes, but for now, they're just holes. We can evaluate f of 0 to find the y-intercept, then simplify if possible. We can find the zeros of the simplified numerator after we cancel the common factors by solving the numerator equals to 0. Those are the x-intercepts. We can find the zeros of the simplified denominator, so after we cancel the common factors, and these will be our vertical asymptotes when the denominator is 0. We check the horizontal asymptote by comparing the degrees of the numerator and denominator, and we plot more points as needed. At least 1 point beyond each x-intercept, beyond the vertical asymptotes. We're going to use smooth curves in order to complete the graph in each part that we have. Let's take a look at this. Alright. Oh, before we get there, this is the one. Hit pause. Hit pause because denominator not 0 is domain. First thing I check. I factor my numerator and denominator, and where they're both 0, the common factor is where there's a hole in the graph. Denominator is 0, but numerator is not. It's going to lead to a vertical asymptote. Denominator not 0, but the numerator is, will give us an x-intercept. And think about it. The y-intercept, if x value is 0, everything except the constant terms will cancel out. So a little cheater's method here, the y-intercept is always the value of the constant terms. And for the horizontal asymptotes, we'll check the degree of the numerator and denominator, but frequently those are leading coefficients if the degrees are the same. Alright, so sketch the graph of the rational functions. We'll kind of have some highlights along here. Numerator, if that's where it comes from, in a light blue. Denominator in yellow, and green if it comes from both the numerator and denominator. If f of x equals x plus 1 over x squared minus 1, I'm going to look at my domain here. X squared minus 1 cannot be 0. So x cannot be negative 1 and positive 1. And maybe you're able to see that. Maybe you need to see the factored form to see why that happens. Either way, it's going to come from just the denominator to tell us the domain. I have a common factor. Let's use green. I have a common factor of x plus 1. This is going to lead to a hole. A hole at x equals negative 1. So the x plus 1 as a factor set equal to 0 will give me a hole at x equals negative 1. Now that I have those simplified, I can look at the simplified version. I know I'm going to have a vertical asymptote at x equals 1. I know my numerator is never 0, my simplified numerator, never 0, so no x-intercepts. I can go back to the original and see that my y-intercept, when x is 0, I'll have 1 over negative 1, so 0 comma negative 1. The degree of the numerator is less than the degree of the denominator, and so y equals 1. That's not true. That should be a y equals 0. I think it says y equals 0 because I do have it graphed here correctly. But let me make sure that it reads y equals 0 as well. Looks like I put a graph over top of that. So horizontal asymptote of y equals 0. Sketch in your vertical asymptote. All right, it's where the denominator is 0 after the simplification. Sketch in your vertical asymptote. Horizontal asymptote. I have a y-intercept at 0, negative 1. What does this hole mean? It means it's an open circle on the graph. And although we cannot put negative 1 in the original function, this will get 0 over 0, which is called an indeterminate form, we could put negative 1, this problem spot, in over here. 1 over negative 1 minus 2 gives me negative 1 comma negative 1 half. That's the location of my hole, and I graph it as an open circle. Now, in order to get the true flavor of this portion of the graph, I picked in some random points. I have no idea what's going on over here, so I picked x equals 1.5, x equals 2, maybe an x equals 3, and I could get the shape of the other side. If f of x equals x squared minus 4 over x squared minus 3x plus 2, the first thing I'm going to do is factor the numerator, x plus 2 times x minus 2, and factor the denominator, x minus 2 times x minus 1. I can once again see I have a common factor. Common factors always give me holes. So I have, for my domain, x cannot be 2, x cannot be 1, because they make the denominator 0. My hole is what they have in common. The common factor of x minus 2 turns into a hole at x equals 2. Moving to the simplified version, x minus 1 in the denominator tells me a vertical asymptote, the equation x equals 1. And x plus 2 in the numerator tells me I'll have an x-intercept at x equals negative 2, a factor, leads to the 0, so negative 2 comma 0. Back to the original, my y-intercept is going to be negative 4 over 2 because the x value is of 0. Negative 4 over 2 gives me a y-intercept of 0, negative 2. Degree of the numerator and degree of the denominator are the same, so the leading coefficients, 1 over 1, or y equals 1, will be my horizontal asymptote. So I plot my vertical asymptote, x equals 1, my horizontal asymptote, y equals 1. I have a y-intercept of 0, negative 2. I have an x-intercept of negative 2, 0, and that gives me a pretty clear image of what's going on. I have a hole at 2, so if I put 2 in the original function, I'll get 0 over 0, which means I'm going to put it in the simplified version. If I put in 2, 2 plus 2 is 4 over 1, so at the x value of 2, open circle on 4, Let's take a better look at that. That's supposed to be an open circle there on, let's see if I can get this back in the right spot. Call that good enough. An open circle at 2 positive 4. And then I need to know a little bit more about this part of the graph, so I just use an extra point, 3, 2.5. It's a basic rational graph that has been shifted a little bit, both right and up. If f of x equals 1 over x minus 3, there's nothing to simplify here. The domain x cannot be 3, so the vertical asymptote x equals 3. Numerator has a smaller degree than the denominator, so horizontal asymptote is y equals 0. The numerator is never 0, so no x-intercept. When x is 0, y value is a negative 1/3. There's no common factors, so there's no holes. I don't know much about this graph. I have x equals 3 as the vertical asymptote and y equals 0. I have the value 0, negative 1/3, but I'm going to use quite a few extra points to determine what my graph is going to look like. It's important to keep in mind that not all graphs will be like this. It could be that the graph was down here. And that's why we plot these extra points. Is the graph above or is it next to? So make sure you plot those and you don't just assume it's going to be up here in the other moved part of the quadrant of the graph. For 1 minus 2x over x, no common factors. The domain tells me x cannot be 0. This also tells me the vertical asymptote, x equals 0. No common factors, no holes. X-intercepts occur when the numerator is 0, and the numerator is 0 at an x value of 1/2. When x equals 0, I'll have 1 over 0, which is undefined, so no y-intercept. Degree of the numerator is 1, degree of the denominator is 1, so I look at my leading coefficients, negative 2 over 1, and if it helps you, feel free to rewrite this as negative 2x plus 1 all over x, so that you can see exactly where your leading coefficients are, negative 2 over 1, so y equals negative 2, x equals 0. Anytime you have a vertical asymptote of x equals 0, you will not have a y-intercept in this class. Plot some points. I do have an x-intercept, and it looks a lot like our other ones, just shifted in different ways. Example 5. f of x equals 2x squared minus 5x minus 3 over x cubed minus 2x squared minus x plus 2. If you were to factor this, the numerator factors as 2x plus 1 times x minus 3, and the denominator factors as x minus 2 times x minus 1 times x plus 1. If you need to, hit pause, make sure I factored that right. Hint, I did. Okay, so I see no common factors. There's nothing in the denominator that also appears in the numerator. First thing that tells me, no holes. The second thing it tells me is that once I get my domain, x can't be 2, x cannot be 1, x cannot be negative 1, I also have my vertical asymptotes. And where in the domain I can list them as a series of values that I'm excluding, for vertical asymptotes I have to list them as equations of lines. So it's x equals 2, x equals negative 1, x equals 1 because these are equations. The degree of the numerator is 2, degree of the denominator is 3. Since the numerator has a smaller degree, y equals 0 is our horizontal asymptote. X-intercepts occur where the numerator is 0, and this is where factored form comes in super handy. A negative 1/2 and a positive 3, negative 1/2 and a positive 3 are going to give me my x-intercepts. Y-intercept at negative 3/2, so 0, negative 3/2. No holes because there are no common factors, and I don't have much at all. I have this vertical asymptote, an x-intercept and a y-intercept, but does it come back up or does the graph go down? I have nothing over here. I have no idea what's going on in between these vertical asymptotes, and I have an x-intercept, but what happens to the graph after that? For this particular graph, we need a lot of extra points, and these extra points fill in the shapes. This one was easy to miss. It's a nice little almost parabola looking thing in between x equals 1 and x equals 2. And notice over here that our graph does cross the horizontal asymptote, but remember, the horizontal asymptote is end behavior. Eventually, as x gets large enough, the y values go to 0. Might be negative, might be positive, might be 0 at some point before that. But as x goes to positive infinity, the y values will approach 0. This is a challenging graph, but you could totally do it. Alright, so far we've only discussed horizontal and vertical asymptotes. There are many other types of asymptotes. But the last one we're going to discuss here will be linear asymptotes, which are frequently called oblique asymptotes, or slant. I like the word slant better because oblique is kind of an obtuse word. If the degree of the numerator is exactly 1 more than the degree of the denominator, the graph of the function has a slant asymptote. To find it, we're going to divide and look for the quotient. So if f of x equals x squared plus 5 over x, I can rewrite this. Notice the degree 2 is exactly 1 more than the degree of the denominator 1. That's x squared over x plus 5 over x. And when I simplify, that'll be x plus 5 over x. We're going to ignore the remainder. The quotient, x, y equals x, is the slant asymptote. That's it. If I have x squared over x minus 1, I can't do this neat little split it trick, so I'm going to use synthetic division. A factor of x minus 1 leads to a 0 of 1. I have 1x squared in my numerator, 0 x's and 0 constants. Remember with synthetic division, very important to fill in zeros all the way down. Synthetic division, bring down the 1, multiply to go up and over, add straight down. Multiply to go up and over, add straight down. We don't care about the remainder. The slant asymptote will always be y equals, and then in this case, 1x plus 1, slant asymptote. Let's do one more. If f of x equals 2x squared minus 5x plus 5 over x minus 2, okay, we know a vertical asymptote of x equals 2. We see the numerator has a larger degree of the denominator, so no horizontal asymptote. But the numerator of degree 2 is exactly 1 more than the degree of the denominator, which is 1. So I know there's a slant asymptote I can divide. The factor of x minus 2 turns into the 0 of 2. Coefficients 2, negative 5, and 5. Bring down the 2, multiply to go up and over. Negative 5 plus 4 is negative 1. Multiply to go up and over, but you don't have to because we don't care about the remainder. I just have a hard time leaving my division unfinished. So 5 minus 2 is 3. I ignore the remainder. My slant asymptote is y equals 2x minus 1. Always an equation of a line. Never just an expression. 2x minus 1 is not an asymptote. It's a factor. Y equals 2x minus 1 is a slant asymptote. That's all I have on rational functions for now. Thanks for listening.